Good morning, friends. In the previous video, we looked into virtual threads with thread per client request and thread per order passing OMS, in which we saw that the throughput was tremendously increased. We tried to connect with 10,000 client connections, socket client connections at the same time, and we saw that it was all served properly. And each thread, each virtual thread, or each client request was handled each for 4 seconds. So if we just revise it again, essentially when we were using platform threads, and then we came up with 7 approaches where we talked about various different type of techniques by which we can increase the throughput or the latency of our OMS server that we are designing. So using virtual threads, we actually combined the second approach in which we were creating one new thread for every client socket request, but it was marred by by the number of threads that we can create, by the limitation of the number of threads that we can create, platform threads, because of the limitation on the OS kernel threads which are there. So this was the first with the issue with this approach, the number of threads that we can create. And other thing, the other good thing that we did in that another third approach was that we're creating multiple threads for order parsing, validating, and persistence. So for this, all these 3 parts could be done in a concurrent way so that it reduces the latency. So we combined these 2 approaches with using virtual threads. Because virtual threads, if we are having a new virtual thread created for each client request coming, because as we know that virtual threads are quite lightweight as compared to the platform threads, and there is no limitation as such for virtual threads. That's why we were able to scale it. We were able to have a very, very good throughput. This was the previous class. We can check our previous video in which I discussed this in details, but just have a quick recap here. So whenever we have a client server socket accept method call, so we have got a new client request here, and this client request, every time for each client request, we were creating a new virtual thread, Thread.startVirtualThread, and inside that we were handling that. So this is the handle part for each of the client requests, and then our main thread will again go back here and then accept for the next connection. In the handle method, it's quite much similar. It's quite similar that what we did before the platform threads, but let's revise it again. That this is going to take one second for creating the request from the socket, and after that another 1 second to create the order object out of that request. And then we do 3 parallel operations on virtual threads again, Thread.startVirtualThread for validation, enrichment, and persistence. So by running these 3 threads concurrently for all these 3 operations, so we reduce the time. And the only thing that we are going to use here, that we are using calling the join method, which means that all the order objects and everything should be thread safe. So this is one small caveat, that we have to synchronize all our order methods here because we are calling the join method. And finally, we send it to the downstream. So this was all good. We were able to have the latency of like say 4 seconds. So 1 second for this, 1 second for order, and then because this is all concurrent, so it's like another 1 second, and then finally the 4th second for sending the order to the downstream. So it took around 4 seconds. So if we go back here, throughput was tremendously increased. Now we saw that even more than 10,000 client socket connections at the same time, we were able to handle it. There was no exception, everything was fine, and it was quite fast as well. So, but for the caveat, as we discussed, that because this needs to be thread safe, because we are using all those 3 threads for concurrently validating, enriching, and persistence. That's why we have to ensure about the thread safety here. And also, we saw that in our previous approach with platform threads, we were able to reduce the latency from 4 seconds to even less than 3 seconds by using the futures. So this is something that we can use with the virtual threads, which we are going to discuss today. That we can further enhance it. So we can still use virtual threads as before. We can, every time we get a client request, we create a new virtual thread. So throughput would be intact. But to further improve the latency from 4 seconds to 3 seconds, we can combine with the virtual threads with Futures OMS. So again, let's discuss what was the problem before. So there was only one drawback. Order must be thread safe again and needs to be constructed before the validation, enrichment, and persistence are started. This was the only caveat. Although you see that there is a join method being called, so I'm calling a join method here, but still it's different than the normal platform thread join, because that here when a virtual thread invokes join on a thread that is still running, it does not block the underlying OS thread. This is the main difference with the platform threads and the virtual threads. The join is like quite lightweight here as well when we are using virtual threads. It will not block the underlying OS thread. So let's further improve our design, improve the latency by using virtual thread with Futures OMS. This is the class that I already designed. So the first part here is exactly same, that whenever we get a client request, for each client request handling, there would be a new virtual thread created. And because if we have got like 10,000 plus client requests coming at the same time, still, because the virtual threads are very lightweight, it doesn't need to be limited by the number of kernel threads that we have, because it has got this mounting and unmounting behavior on the platform threads that we have, which are having one-to-one mapping. That's why we can create lots and lots of virtual threads. I have talked about this in all details in the previous videos, so I will not go through it again. But just know that virtual threads we can create a lot of virtual threads, and it's not limited by the number of OS kernel threads that we have. Let's talk about the handle part, where we are trying to use CompletableFuture to further reduce the latency from 4 seconds to 3 seconds. So again, we have talked about this in details here with features with composition OMS and callbacks OMS. So it's exactly same. We are just using it in context of virtual threads. Okay, so first of all, it will take 1 second. We'll create our request object out of the socket, and after that, we just create these 3 CompletableFutures objects for validation, enrichment, and persistence. Please note that right now it doesn't need to be having order in invokes. So for each of these 3 operations, we only need the request object. We don't need the order object at all. So again, so once we create this CompletableFuture object, this is what I'm creating 3 new virtual threads definition here. Please note that I haven't started it yet. I'm just creating this virtual threads, and here the lambda or the enable that is defined here, it is just that we complete on this validate method or enrich method or persist method. When we click on this, so this will actually give me the order object back, and I've just mimicked it it will take around 1 second. So this is what we need to understand here, because we created a CompletableFuture object with order as our generic element inside it, and then we define it that we explicitly call complete method, in which for each of them it will validate, enrich, and persist in all these 3 virtual threads, and then return the order object out of it. And this is my main the operation that I'm going to do. So here now I'm creating the new order object request, and all these 3 can be run in parallel, because it just needs the request object. What it also means is that all these operations, like creation of the new order, and all these 3 operations are like quite quick, that it appears that it's all runs in parallel. So it will take 1 second here for creating the new request. All these 4 operations, like creating the new order from out of the request object, and all these 3 operations can all be done in parallel. So 1 plus 1 again, 2, and then finally we send the order to the downstream. The order to send to the downstream, this is 3 seconds. So this will take only 3 seconds as opposed to 4 seconds that it was without the Futures OMS, in which we just use the imperative style progress type to create and join. So this is the power of CompletableFutures, and this is also, we can say that this is a sort of features with composition, with composition, right? So using a sort of like composition algorithm here, in which we have further reducing the latency to like 1 by 1 second. So again, now we have got the perfect OMS design, in which the throughput is very, very high, because every time we get a new client request, we're creating a new virtual thread. So throughput is totally increased, and also we are able to reduce the latency from, like, say 6 seconds. Each of these operations takes 1 second each, like creating a new request object, creating the validation, enrichment, persistence. So I mimicked it for taking like 1 second each. So if I just go through the imperative style, it will take 1 second each, total 6 seconds. But using virtual threads as well as CompletableFuture, we are able to reduce it from 6 to 3 seconds. This is all theory now. Let's run this program and see that whether it actually works as we expect. So let me run this. You can also use Ctrl+Shift+F10 as a shortcut key. So once it starts, it will be listening on this port 8080. Okay. So let's start with the simpler one, so that I will connect with four concurrent client connections at the same time. So again, I mean, I think I have been just running through it. Let me to quickly go through it. That this is a socket client class that we created before. And if I just go up here, so whatever arguments that you are passing, so I'm passing like 4 for this. And if I want to pass like say 10 or 10,000, whatever, that the number of sockets to create. And every time it will just try to create this and connect to our 8080 port. And then it will take like 1 second each after it has done all the connections. And then finally it will disconnect. This is my design, okay? So whenever I say socket client 4, it means that I'm going to send 4 socket connections at the same time on port 8080. So as we learned that this program will actually create 4 virtual threads for handling all these 4. Let me run this quickly. Okay, so as soon as I run on socket client 4, so there will be 4 socket client connections connected. And as you can see, it's very, very fast. And as expected, it's taking only 3 seconds. In the previous example, when we were not using Futures OMS, CompletableFuture, in that case, it was taking 4 seconds. So it's now 3 seconds each. Now let's do the heavy flow that we are going to send 10,000 collections at the same time. Let me run this. If we go through the platform threads, which we have seen that it will just take like 2,000, 3,000, and then it will be gone. It will throw some exception. It's not able to create or handle so many threads at the same time. But here in Future, you can see that it's very, very fast. I just solve this going on. And I can see that 3,000 something are already done. So it's very fast. And it's actually all of them are taking around 3 seconds each. Okay, so it's all connected now. I can see disconnected methods here. So as you can see, 10,004 because the 4 one was previous, and now we have got another 10,000 requests all done, and it was all 3037. Guys, one thing note here that I haven't paused anywhere in my video. It's all exactly when we are talking. It's able to handle all these 10,000 requests in the very live streaming that I'm doing right now. So this is the benefit of using virtual threads. All went so well. Each of the client requests is taking only like 3 seconds around to send out to the downstream. So yeah, this is the demo for this is I would say that the perfect design for the OMS. I mean, I've just mimicked it for all this. Like it will take 1 second for 1 second. I mean, of course, in the actual use case when we are actually building a OMS server. So there would be a lot of operations which can take multiple type of variable time. But using this demo, what I wanted to demonstrate is that the throughput can be increased. First of all, the throughput in which we are measuring that how many client requests can be served at the same time, that can be tremendously improved if we just use a very simple virtual thread model. Every time we create a new virtual thread, whenever it is called. So whenever we actually receive a new socket request, we can create a new virtual thread. This is a very simple design as well, and it will it is able to handle, as you have seen, that more than 10,000 threads connections at the same time. And similarly, by users of CompletableFuture also, we see that we can have a very, very nice design, a similar type of design where we can compose all our design and reduce the latency from say 6 seconds to less than 3 seconds. So a few more points for virtual threads. There is no improvement in latency, but only throughput. When we're using virtual threads, as we have seen here in our design, that we are not actually, virtual threads will not improve any latency. We still have to use, say, CompletableFuture to and the different type of paradigm that we have used, like with compositions and callbacks type of design. But that is all based on CompletableFuture. That can be done similarly for platform threads as well. So virtual threads are not for improvement in latency, but only throughput. Because they are lightweight, we can create many, many virtual threads at the same time. This is the one thing that we need to know. Another thing is that virtual threads are always daemon threads, which means that trying to set it to non-daemon will result in exception. So daemon threads mean that if we are going to shut down our main program goes down, in that case, virtual threads will be also all shut down. Virtual threads should never be used as fixed size thread pool. Because if we are trying to like fix size, then the whole benefit of using virtual threads would be gone, right? With that's what we saw when we are using exhibitors.fixed thread pool and all, because we are limiting the throughput to overall. Virtual threads are designed for that. they are designed to be like to have a lot of virtual threads so that we can increase the throughput in all these type of scenarios or the use cases. So it should never be used as a fixed size thread pool. And virtual threads should always have default priority. As you know that we can set the priority for the platform threads, but virtual threads, they have their default priority, and if you try to change it, then it will have no effect. These are the 4 things that we need to just other points to note about the virtual threads. So guys, we have gone through a long way with the project Loom about the virtual threads, in which we discussed a lot of topics in details, and I totally enjoyed it. In the next video, we'll resume our discussion about the scope values, which still comes under the project Loom. And after that, we will follow up with the structured concurrency. So see you all in the next videos.